Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. We are now discussing Module 5, Alcohols and Ethers. In Lecture 2, we will be studying about reduction and the Grignard reaction for the preparation of alcohols. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The various topics that we will be covering in this particular session include reduction methods using different metals for the preparation of alcohols. We will be studying about sodium and transition metals also, which are involved in the reduction methods. And we will also be studying about application of Grignard reaction for the preparation of alcohol. So how primary, secondary and tertiary alcohol can be prepared using Grignard reagent. Let us quickly compare some of the reduction methods that are used for the synthesis of alcohol. First, let us study about the sodium and ethanol reaction, that is the Bois-Blanc reduction. So here aldehyde, ketone or esters are reduced in the presence of sodium and ethanol. This is a single electron transfer reaction. So in this particular case, what happens is sodium is converted into Na plus ion and electron. So this is what is the single electron which is involved in the transfer reaction. We will see the entire mechanism later, but now we will simply compare the different methods. So in this sodium ethanol method, it is a single electron transfer method. So according to the electron transport, what we can say is loss of electron is oxidation and the gain of electron is reduction. So in this particular case, this electron is gained by the starting material, aldehyde, ketone or esters. So that is why this reaction is called the reduction reaction. And the next one is the catalytic reduction. The catalytic reduction generally uses hydrogen with platinum or palladium and hydrogen with Raney nickel. So these are all the various metal catalysts which are used along with hydrogen for the reduction. So this catalytic reduction is aldehyde to give the corresponding primary alcohols, and when we have the alpha beta or the unsaturated aldehydes and ketones, they undergo both the reduction of the double bond and the carbonyl group. Both are reduced depending on what is the catalyst we are using, and so we have the completely reduced alcohol is formed in this particular case. And when we take benzaldehyde as the substrate, this also undergoes reduction with Raney nickel to give corresponding reduced derivative. So the next one is the hydride reduction. Either sodium borohydride or lithium aluminum hydride is used. So in this particular case, so aldehydes are reduced with sodium borohydride to give the primary alcohol. Esters are reduced with lithium aluminum hydride to give the corresponding primary alcohols. So these are all the three different reduction methods for the carbonyl compounds. And here we have both the carbonyl compound and the alkene is also present. So any of this method can be used for reducing to get the corresponding alcohols. Why it is difficult to reduce the carboxylic acids or the COOH group using hydride reducing agents? The answer is actually due to the resonance delocalization of the carboxylic acid. Due to the delocalization, the electrophilicity of the carbonyl carbon is actually reduced. So in the resonance structure, what we see here is the lone pair is shifted to this double bond and the electronegative oxygen pulls the electron towards itself. So we have a double bond from carbon to oxygen, the oxygen is having a positive charge and this oxygen is having a negative charge. So in the first structure, we have a carbon, the carbonyl carbon with a double bond here, and in the second structure, the resonance structure, again the carbonyl carbon still has the double bond. So that means the electrophilicity of this carbonyl carbon is not reduced, it remains the same in the carboxylic acids. So this carbon, which actually undergoes hydride reduction, is less electrophilic in the case of carboxylic acid. So that's the reason hydride reducing agents cannot add to this particular carbon, because basically this is a nucleophilic reducing agent. The nucleophile is the hydride is the nucleophile. For the hydride to add, we do need a electrophilic carbon, and the carboxylic acid, the carbon is not highly electrophilic. So due to that, borohydride reducing agents cannot reduce carboxylic acids. Whereas in the case of simple ketones, if you look here, the double bond electrons are pulled toward the electronegative oxygen. So we have a delta negative charge on this oxygen and we have a delta positive charge on this carbonyl carbon. So this carbon is more electropositive compared to this carboxylic acid carbon. So that's the reason ketones are very readily reduced by hydride reducing agents, whereas carboxylic acid is not reduced by hydride reducing agents. Let us look at how borane can reduce carboxylic acid. So this is the carboxylic acid and this is the borane. So borane can reduce the carboxylic acid, whereas sodium borohydride cannot reduce the carboxylic acid. So now let us look at how the reaction actually proceeds. So in the first step, we get a boronic acid ester. So alkyl boronate ester is formed in the first step with the liberation of hydrogen gas. So this hydrogen is removed and one hydrogen from the boron and the carboxylic acids, the acidic hydrogen, these two are liberated and the oxygen and the boron now forms the bond. So like that, boron has 3 hydrogens, so all the 3 can be replaced by the 3 carboxylic acid units. The carboxylate unit can be added to the boron to give this boronate ester, and with the liberation of 3 hydrogen gas, 3 molecules of hydrogen gas. So this particular, let us look at one of this particular ester part. So this ester part can be reduced by the hydride transfer using this borane. That is, in this particular reaction we have to use large excess of borane for this reaction to proceed, because here one molecule is required for the conversion of the alkyl boronate ester and the second molecule is required for the reduction of this alkyl boronate ester. So here the hydride is transferred from the boron to the electrophilic carbon, and this oxygen bond is the double bond between carbon and oxygen is bonded towards the boron. So this is repeated couple of times because the alkyl boronate has, this boronate ester has 3 substituents, so all the 3 has to be reacted with this borane. So we repeat 3 times and we get this particular intermediate is formed, where the boron has 3 oxygen bonds and the hydride is actually transferred, 1, 2 and 3 hydrides are actually transferred, and this one on hydrolysis in the presence of acid produces the corresponding aldehyde, and hydroboric acid is also formed. And this aldehyde is very similar to our starting material. So this again can undergo reduction using the hydride. So here in this particular case, we again get the same alkoxide type derivative is formed. In this particular case, the boron forms the oxygen bond. See, this boron and this oxygen, they both bond together with the removal of 3 hydrogen atoms. The same way we get very similar to this type of intermediate is formed. In this particular case, here we have only one hydrogen, and in this intermediate we have 2 hydrogens, and this again can undergo hydrolysis in the presence of HCl to give, or any acidic reagent to give the corresponding primary alcohol. So from the carboxylic acid we can directly get the corresponding primary alcohol using this borane reducing reaction. We saw the carboxylic acid group can be reduced using borane, but we cannot use this procedure for the reduction of esters. Let us see the reason why we cannot reduce esters using BH3. Because in the just seen mechanism, what we have seen is the borane forms a acyl boronate esters with the liberation of hydrogen gas. So this is the first step we had seen. So this intermediate, the acyl boronate ester on acidic hydrolysis gives the aldehyde, which can further be reduced to the alcohol. So for this particular case, we need an acidic proton. So in the first step, the acyl boronate ester formation requires the acidic proton. But in the case of esters, we do not have that acidic proton. So that is the reason esters cannot be reduced using borane. That means only the carboxylic acid group can form the acyl boronate ester. You can assume like this, because the carboxylic acid is the acid group and the borane BH3 acts like an alcohol. You can assume like that. So in that case, H and this hydrogen both are removed to form the corresponding acyl boronate esters. But in the case of COOR, that means ester group, we do not have a hydrogen but we have a R group. So that's the reason esters cannot form the acyl boronate bond, ester bond. So that's the reason esters cannot be reduced by boranes, whereas carboxylic acid can be easily reduced. So it is possible for us to chemoselectively reduce a carboxylic acid group in the presence of a ester group. So it is possible to chemoselectively reduce a carboxylic acid group in the presence of a ester group. This is the last synthesis for alcohols. So this is the hydroxylation of alkenes. So alkenes can be hydroxylated using osmium tetroxide in the presence of hydrogen peroxide, or KMnO4 in the presence of a base. These are all the 2 different reagents which can be employed for the dihydroxylation of alkenes. So this leads to the formation of diols. So this diol is nothing but a glycol. So the glycol can be formed. So in this case, an alkene can be converted to glycol by treatment with osmium tetroxide in the presence of hydrogen peroxide, or KMnO4 and strong base. Basically, hydroxides can be used to make the diols. And let us look at the hydrolysis of alkyl halide reactions. So the first one is the reaction with aqueous alkali. So when we talk about an alkyl bromide, when it is treated with the sodium hydroxide, we can get alcohol as the product. So this is one of the method for the synthesis of alcohols. And when we have a secondary chloride, when treated with the sodium hydroxide, we have 2 types of reaction possible. One is the substitution reaction by SN2 mechanism. Another one is the elimination also occurs in this particular case. So even though, because aqueous alkali, basically the hydroxide ion is a very strong base and it is also a strong nucleophile. So being a strong base, this facilitates the elimination reaction also. So that means we have a very limited use of alkyl halide treatment with aqueous alkali to produce alcohol. because not all alkyl halides can be used for the preparation of alcohols using this method. So the major limitation is the competitive reaction between the substitution and elimination. So we have to identify a better reagent for this particular conversion. So we have a better method where alkyl bromide, when treated with silver oxide in the presence of water, produces alcohol, and here the silver halide is formed as a precipitate. So in this particular case there is no elimination possible because we do not have a very strong nucleophile like the hydroxide minus ion in this particular case. So that's the reason we have a, and moreover the silver halide which is formed is precipitated out, in other words, that is completely removed from the reaction system. So this produces the alcohols in very good yields.
Now we will look at the different methods of alcohol synthesis. The first reaction is the nucleophilic substitution of halides with hydroxyl ions. Next one is organometallic reactions, basically the Grignard reaction. This is a very famous reaction. We will see this reaction little bit in detail. And then another important reaction is reduction of carbonyl compounds. Carbonyl compounds can be reduced, or even carbonyl compounds include aldehydes, ketones and esters can be reduced to get the alcohols. And another thing is preparation of alcohols from alkenes. So the conversion of alkenes to alcohols can be effected by hydroboration reaction. So these are few reactions. There are many more reactions which are available for the formation of alcohols, but we will be looking at these two reactions now. And if you look at chemical methods, there are various types are there. One is another one is a reduction reaction. Another one is a hydroboration reaction. Examples of the RX, that is alkyl halides with M, metal and a carbonyl compound. So alkyl halides, metal and a carbonyl compound all together condense to give carbonyl alcohols. Reduction means we take carbonyl compounds, aldehydes, esters with a hydride reducing agent to get alcohols. In the hydroboration reaction, the starting material is alkene. So we have three different starting material. Let us say alkyl halides, aldehydes and ketones and alkenes to give the same product, alcohol. And if you look at the condensation reaction, two major reactions are Grignard reaction and organolithium reaction. The Grignard reaction can be run with the help of halides, esters or acid chlorides. For finding out this reaction, Victor Grignard received the Nobel Prize. So the reaction is a simple reaction in which a methyl magnesium bromide, when reacted with the carbonyl compound, produces alcohols after hydrolysis. So this is a simple reaction, and we will see what are all the different steps involved in this. The first one is the formation of carbon metal bond followed by charge polarization. Then the nucleophilic carbon will attack the electrophilic carbonyl carbon. A new carbon-carbon bond will be formed. Finally, the hydrolysis leads to the final product. So if we look at the general formula and the reactions, RX, the X generally is a bromide which is highly reactive. In fact, iodides are even more reactive than bromides. The Grignard reagent can be formed from primary, secondary, tertiary, aromatic, allylic or olefinic halides. Here, bromobenzene in the presence of magnesium gives methyl magnesium bromide. And for the preparation of primary alcohols, the starting material is Grignard reagent with formaldehyde. You remember, formaldehyde is very important for the synthesis of primary alcohols. And for the secondary alcohol, it is any aldehyde. So remember, it is any aldehyde that gives secondary alcohol with the Grignard reagent. And the ketone gives tertiary alcohols with Grignard reagent. So when we recap The reactant is the same alkyl halide. When it reacts with formaldehyde, that is the carbonyl counterpart, it gives primary alcohol. When it reacts with an aldehyde, it gives a secondary alcohol. And when it reacts with the ketone, we get the tertiary alcohol. So these are all the three important substrates for the formation of alcohols. And if we look at Grignard reactions of acid chlorides and esters, there is a little difference here. Instead of 1 equivalent in the previous reaction, here we need 2 moles of the Grignard reagent, and the product is always a tertiary alcohol with 2 identical alkyl groups. So this is the one you have to remember. When we run a Grignard reaction with acid chlorides or esters, we will be using 2 moles of the Grignard reagent and the product is a tertiary alcohol. Let us look at the mechanism of this reaction. So the first step is very similar to the one which we already know about the alkyl halides. So in this case what happens is the acid chloride or ester or whatever may be the carbonyl substrates reacts with the methyl magnesium bromide or the alkyl magnesium bromide, gives an intermediate to give a ketone. So this is the first intermediate that is formed when 1 mole of the Grignard reagent reacts with the acid chlorides or acid esters. The first product is the ketone, and this ketone undergoes further Grignard to give the final product. So this ketone again undergoes reaction with 1 more magnesium halide to give the intermediate, which undergoes hydrolysis to give the tertiary alcohol. So this is the difference between 1-step and the 2-step process. Although we say Grignard reagent is an important reaction, there are few limitations associated with this Grignard reaction also. We will see. The first one, waters or other acidic protons like OH, NH, SH, etc. generally kill the Grignard reagent. That means they decompose the Grignard reagent, and that's the reason we cannot use these substrates in the Grignard reaction. And another problem is the addition of Grignard reagent to multiple bonds. If we have C double bond N, C triple bond N, or other multiple bonds are present in the molecule which undergo reactions, Grignard reagents cannot be used in those reactions. So these are all the major drawbacks of the Grignard reaction.
So in summary, we have studied about the reduction using different metals for the preparation of alcohols. Basically, the sodium was used for the Bois-Blanc reduction, and the various transition metals were used for the reduction of carbonyl groups. And we also did a comparison between ester reduction using lithium aluminium hydride and acid reduction using borane. Why acid cannot be reduced by LaH and how acid can be reduced by borane are the two things we have studied. And we also have studied about various application of Grignard reagents. Basically, formaldehyde gives primary alcohol, and aldehydes other than formaldehyde gives secondary alcohols, and ketones give tertiary alcohol. So all those methods we have studied in this particular session. With this, we conclude this session. Thank you.